Hello, my name is Danesh Shamsi, and this is my video lab report for Lab 1 of constant velocity motion. The object that I observed was my friend riding around on his scooter in a straight line at a constant velocity. So I uploaded the video to the tracker software that was provided in our class, and I set the origin to the center of his scooter. I have the scooter moving in the positive x direction. Using the calibration tool, I set the length of the calibration tool equal to the length of the base of the scooter, which was 0.6731 meters. Now, I plotted each frame, and I was able to get a set of data that relates time. T in this T column is time, and the displacement is this X. So I copied and pasted all of this data into an Excel spreadsheet. Now, in order to calculate the velocity, because we're assuming this is because it was a constant velocity, it was initial position minus final position minus initial position over the total delta T, change in time. And I obtained a velocity of 3.547 meters per second approximately. Now, we wanted to model this in our computational model that was provided in class. So in order to do this, I set the position vector equal to the 0, 0, 0, and the velocity positive 3.547 in the x direction. Now, I ran this, and is seen that the velocity is constant on this time distance graph, because the slope of a time distance time graph will show the velocity. The reason why this worked was because we used the momentum principle. Because we assumed F net is 0, that means acceleration is also 0 as well. So the velocity never changed in this momentum principle section right here. So what did change was the ball's position. So the ball's position equaled the previous ball's position in this while loop of the ball's velocity times the change in time. So overall, it would show the change in the ball's position for the time obtained in the experiment, 2.332 seconds. That was the total time it traveled. Now, I took the data that was exported from running the computational model and put it in the same Excel spreadsheet as the experimental model. And I made a scatter plot of the experimental model's data represented in the blue dots and the computational model represented in the red dots. So you can see in our distance time graph that they are extremely similar, so the computational model did a very good job of simulating what happened in real life. Now, the reason why this is in the going positive is because I selected the origin to be to set the origin and the traveling way that he was going in the positive x direction. If I was to change this in a tracker, it would have to be changed additionally in the computational model by simply making the velocity negative. Doing this would show right here that it would show a constant velocity, except it would be in the negative x direction. This shows that it's consistent, even though if you were to change the direction that he was going based on the origin. Additionally, the reason why the computational model was so successful was because the F nets were 0, therefore the velocity is constant. Obviously, in actual life, a lot of forces are occurring that make the F net constant. But because in the simulation, in the actual occurrence of the scooter rolling, there was such a number of forces that were actually making the F net equal approximately 0 that it would be inconclusive to just count the number of total pushes and pulls occurring on the object rolling across the screen.